Let's continue with the contrast matrices. Now, this is what is T-contrast vector matrix with zero values. Let's imagine that we have three conditions, and this contrast includes 1 for the first condition and zeros for two others. This means that the contrast will respond only to the first condition if it has any positive effect. In this case, it is most likely significant, and in this case, it is significant. We don't consider any responses related to the other two conditions, and we don't consider if there is a significant negative response. If we set the same F contrast, the graphical representation will be a bit different. Here it is one gray bar turned positively, and this is a white square with two gray squares. F contrast, as we remember, is much more sensitive. It gives significant outcome in this case, but also in two cases when there is a negative response, negative effect of the first condition. This is quite similar to the contrast with two values of 1, as we had shown earlier. And this is very different. As we can see, now it is a matrix. In the first row, 1 stands for the first value of the first column, and in the second row, 1 stands for second value of the second column. This F contrast is sensitive to any response of either the first condition or the second condition. In this case, the contrast is sensitive to the average effect of two conditions, but only to positive outcomes. This example is of particular interest. Here, the first bar was not significant if it was a T contrast like this. The first bar alone is not significant, but together with the second condition, they provide sufficient effect that it is detected as significant. But of course, if both effects are significant but in different direction, the average is close to 0 and is not significant. And if they are one directional but not positive, in this particular case, it will not be significant either. This F contrast is sensitive to actually all the conditions listed here. Of course, it is sensitive to all the situations when an equivalent T contrast gives significant responses, but also if the directions of the effects for the two conditions are opposite. F contrast also gives significant score. Now we can see several examples of T and F contrast for detection of the difference between the effects of two conditions. This is the T contrast. That tests the hypothesis that the first condition is stronger than the second. Gives more positive outcome than the second one, or the second is more negative. It's totally relative. This T contrast compares one first condition to the average of the second and the third condition. Pay attention that there must be half of the index, not 1 but minus 0.5 for both. The equivalent F contrasts exist, but they have to be written in a slightly different way if there are more than two conditions compared. Here we compare the first and the second condition, and whatever is the difference between the effects of those conditions, it will be detected by the F contrast. Either the first one is greater than the second, or the second is greater than the first. It doesn't matter. The comparison between the three groups is ordered like this. This contrast will detect any difference between the three groups of any directions. Between three of the conditions, sorry. So this is the example of the F contrast sensitivity to the difference between the conditions. Those first and second are not different, and those effects are not different either, but in all those cases there is some kind of difference of any direction. The T contrast is sensitive only to those situations when the first is greater than the second. If you want to detect significant difference in the other direction, like this or that, you will have to place -1 for the first condition and +1 for the second. Now let's talk more about factorial design. The two-factor factorial design allows to test for complete combination of all the levels or categories, in our case, of all factors. In our case, it is factor fame and repetition. When you set factorial design, you don't change at all the design metrics. It is just a different collection of the contrasts, and they can be set automatically by the program if you indicate a factorial design at the stage of the model estimation, or equivalently each of those contrasts can be set manually in the contrast manager, as I will show a bit later. So when there are two factors in the factorial design, you can estimate the effect of one factor, the effect of the other factor, and the interaction of two effects. Let's imagine that in our cartoon example there are two factors. The factor of easiness, which is scaled from different to easy to peel the foods. The effect of the taste, which is from untasty to tasty. And there can be also interaction between the two factors. If you test for the easiness, then you must compare category tasty difficult together with category untasty difficult against the other two categories, tasty easy and untasty easy. The difference between those two categories is the easiness. On one side there are two easy categories, on the other side there are two difficult categories. The same for the taste. On one side we collect tasty categories, on the other side untasty, both difficult and easy. The interaction is a bit more complex. On one side you collect tasty difficult and untasty easy, and on the other side the rest of the groups. I will show you the examples of the positive outcome of those contrasts. The effect of easiness will be significant if both easy categories give greater response than too difficult. For example, it can be consumption of the foods at the party. The easy, both tasty and untasty, are consumed in greater extent than those foods that have to be peeled with lots of difficulties. The effect of taste you can imagine as the preference of the food by the children who don't care about how it is useful. They just want it to be tasty. So they will eat more, both difficult and easy, because they don't care about the difficulties to peel, to clean the fruits. Parents will do this for them, and they will eat less, both difficult and easy fruits that are not, and vegetables that are not tasty. And the interaction is more tricky. You can imagine the situation when the craving for foods, namely a desire to be occupied with eating some fruits in your apartment in big amounts, when you eat one after the other, sort of compulsive consumption, will more likely to happen if the foods are tasty and easy, that you are not distracted by anything, you just eat a lot and that's all. Or if it is untasty and difficult, then it is more interesting to be occupied by cleaning the fruits, and it is a different sort of craving. In this case, there will be a significant interaction. In our factorial design, it is important what is the order of indication of the condition and the factors. In the list of conditions, as in our design, N1, N2, F1, and F2, first, second, third, fourth, the first factor will always be the fame, because it is programmed like this, that the first factor changes slowly. It groups first a number of conditions in one level, and then a number of conditions at the other level. Of course, for each level there must be the same number of conditions. Factor 2 takes the rest. It takes every second condition to each level of the factor. That if the order of conditions is different, like this, N1, F1, N2, F2, it is the first factor that is going to be the repetition, and the second factor will be the fame. So you are free to select the factors and to call them however you prefer. The only important thing is that everything is consistent. The name of the factor is consistent with the conditions which are automatically selected by the factor. Now we have to go to statistical inference, and that's why we need first to estimate the model that is already specified. Remember, our last batch was model specification. Here are the condition and one conditions and 1 and 2, f1, f2. And the first factor is fame. The second factor is repetition. This is already done, and we see the design matrix. You can check the cutoff of the high pass filter and how much the conditions are interdependent. You select the SPM file for the review, and here in the design menu you can explore each condition together with derivatives. This is the time series, and this is the hemodynamic functions. You can magnify it. Those blue dots are the scans. Not really. This is something arbitrary. No, they're not scans. Our scans are S, frequent S. As the 1 per second. And this is the high pass filter. This is what is removed from the design. Quite some activity is removed by the filter, but the rest remains. And you can test for orthogonality. It's good that all the squares in this triangle are pretty pale. If they are dark like this, this means that the conditions are interdependent, which means that it will most likely not be possible to separate the effect of each of those conditions. Let's open the menu and see if the figure looks like this. Yeah, most likely it is the same. Now we have to estimate the model, which is very easy. You just have to select the SPM file. You save the batch. And you run it. And then we will start with statistical inference and the contrast manager. Here in the working window of Matlab, we will see the message done as soon as everything is over. Okay, now we can click results, and again we select the SPM12 file. This is the contrast manager, and all those are contrasts which are already generated automatically by the program. Nonetheless, you can define new contrasts, any contrast you can imagine, and we will do it. But first, let's review all those contrasts and discuss what do they mean. So letter F means that it is an F contrast. You can select only the F or only the T or all of them. F contrast. This contrast is going to test for any effect of any of the conditions, and within the effect, the coefficients for the combinations of the canonical function, the time and dispersion derivatives will be found individually by this kind of F contrast. So this is how we can maximize our sensitivity to detect the event-related responses of all variety of the shapes of hemodynamic functions, hemodynamic response functions. This is the main effect of FAM. Again, whatever is the difference between two levels of the factor, non-famous and famous, it is going to be detected, including the possible variations of the wave shape of the hemodynamic response. This is the contrast to detect any positive or negative effect of the repetition. We compare first presentation to the second presentation with all the two derivatives, and this is the interaction. The contrasts are more simple. Positive effect of canonical hemodynamic response, time and dispersion derivatives, the average of them. This is the non-famous against famous, where the response is greater for non-famous than for famous. This is the difference between the first and the second presentation. This contrast detects the responses which are stronger at the first presentation, whatever it is, the non-famous or famous, and the second presentation of the same image. Let us see the manual and follow the instructions. What do they propose? They propose to take positive effect of condition 1. It is just the average effect of the presentation of any kind of phases. We select it and click Done. For apply masking, we click None. Masking procedure is quite important and we will use it a bit later. For P adjustment, we click FWE. This is family-wise error, another important concept which we are going to discuss when we see the table, the resulting table. So we select significance level as 0.05, 0.05, and no extent threshold. And this is the figures that we have to get, and if we compare it to the figure from the manual, it is quite similar, so not absolutely identical. This figure has a lot of very interesting elements, and we will examine them carefully, starting from top to the bottom. First, let's consider what is at the top side of the figure. Obviously, you know very well that there is a design matrix shown here. This is the graphical representation of the T contrast. This is the name of the contrast. And this is the MIP, maximum intensity projections over the glass brain, where you can clearly see that the most of the activation by the presentation of the faces is located at the ventral occipital cortex, probably around fusiform gyrus. And this is the name of the folder where the results are stored, and the height threshold, which is WFE, FWE, family-wise error, corrected. This means that the results, all the voxels shown in the image, are significant. And the extent threshold is 0. So we include all the responses, even if the cluster of those voxels is just one voxel. And now we will carefully examine the result table, column by column. But first let me show how to move this table to a separate window. We click on SPM figure, we select results table, and in the interactive window you click, for example, whole brain, which will give you all statistics for all the responses detected in the current experiment. So this is pretty much equivalent to this, but let me explain you what is shown in the table. There are a lot of numbers, and they are very useful. Actually, the table is much more useful if you want to understand if the results are significant and relevant or not than the figure, because here everything is quite precise. First, you get a precise location of the maximum of the significance of the response in a given cluster. Those are coordinates in M and I space. This is right to left. This is anterior to posterior. Anterior is positive, posterior is negative, and this is dorsal to ventral, where dorsal is positive and ventral is negative. Here you see the extent of the threshold for T statistics, and you see the rate of smoothing, the total number of voxels, the voxel size, and many other supplementary numbers. Expected number of voxels per cluster, which is how many voxels per cluster are accumulated by chance in this situation. Since we selected everything corrected for multiple comparisons, this extent is close to 1. So even one voxel per cluster is significant. Let's go forward. This is level of P, significance uncorrected. You see, everything is very significant. But this is not what you are going to use when you report your results, because this is uncorrected for multiple comparisons at all, which is not enough when you deal with neuroimaging with thousands of voxels in the volume, which means thousands of multiple comparisons where you can get plenty of false positives. This is what you need. This is the good index of significance, because it is family-wise error corrected for the volume of examination. If you test for the volume of the whole brain, you want to find all the significant activations in the whole brain. The difference between this and this will be quite big. But if you are looking for significant activation in a small volume, let's say only in the left amygdala, and that's all, then the difference will be much less, especially in the smoothed images. And typically the functional images are smoothed. But keep in mind that you always have to report corrected statistics. This is the gold standard at the moment. And this is another important feature of the data you achieve. The significantly activated voxels can be grouped together in clusters. This means that they